Greetings, chemists. We're going to be talking today about a topic called classification of matter. And largely this will be about how scientists, and in particular chemists, talk about different types of matter and what categories they fall into. It's going to be a lot of vocab. So let's actually start with the definition of matter. Matter is basically stuff, but that's a very non-specific term. So matter is essentially anything made up of particles. Okay, it has mass, it has substance to it, right? Light, for instance, is not typically considered matter, although there is a particle theory of light, but light does not have mass. Energy does not have mass, although it is related to mass, right? As we'll find out in the nuclear chapter. So in order to be considered matter, you have to be able to we need to be able to put you in a container, we need to be able to weigh you on a balance, you have to be made up of particles, okay? Particles that have mass. Matter, I should add that in there, matter has mass. At least for the purposes of this class. So, let's take this further. A lot of the ways we classify matter our categories of matter are based on what kinds of forces it takes to break that matter into smaller pieces. What do I mean by that? Let's start with this piece of paper. This paper is matter. I can weigh it, I can hold it, I can put it in a container, and I'm going to break it apart here. Okay? Now, I broke it apart with my hands. We would call this a physical means, a physical separation. I can take this paper and pull it apart physically with my hands. What's going on when I tear it apart? Well, this little piece here, this is a piece of paper. This little piece here, this is still a piece of paper. And as long as I keep doing this and getting smaller and smaller chunks, and I'm using a physical means to break it apart, I'm still getting the same type of material. It doesn't turn into different kinds of matter. Maybe it turns into smaller pieces of matter, but each of these pieces of paper basically functions the same as any other piece of paper. It could be crumpled. I guess they could be burned or lit on fire. They're all pretty much the same, okay? So that's a physical means of separation. So when I use my hands to physically separate matter and break it down into smaller and smaller pieces, a physical separation can separate, in this case, I'm basically putting a certain amount of molecules to one side and a certain amount of molecules. Can separate molecules, but not break chemical bonds. And so now we have some terms in there, right? What's a molecule? What's a chemical bond? We'll get to that, okay? Those are good questions to ask. Maybe I'll write them in the margin. Okay, that's a physical separation. Now, what if I were to take and light the paper on fire? Okay, turns out paper is a complex molecule. If we were to look down at the paper, it's made up of little pieces, okay? There's some carbon atoms, and they're attached to each other with these chemical bonds, and there's some hydrogen atoms, and there's probably some oxygen atoms in there somewhere, okay? And they all kind of connect. And every time I break, let's say this is one piece of paper and this is another piece of paper. I know I'm drawing something here that is not going to be chemically accurate, but it's just to show you. So imagine this was a paper molecule. This acts like one big chunk. And this is another paper molecule, and this acts like one big chunk. And with my fingers, I can reach in and I can pull them apart like this. Okay, that's possible, but generally speaking with my fingers, it's not, I can't really pull the carbons apart from each other. I can't really pull the hydrogen off of the carbon. So a physical separation could move these molecules apart from each other, but could not break a chemical bond, whatever that is, which we're going to have a whole chapter on that later. Okay? What about, so what happens when I burn it? Well, when I burn it, for one thing, a bunch of oxygen atoms are going to come in and attack those bonds, but this process of burning paper actually takes and pulls the carbons out and pulls the hydrogens out. It sticks them to the oxygens, right? And basically will take all of those bonds holding everything together and kind of destroy them. That would be a chemical separation. So a chemical separation can break bonds between individual atoms. What are atoms now? Okay, so now that we have these kinds of, well, let's keep going for one more actually. So keep that in the back of your mind because we're going to talk about what atoms are. Now let's suppose that I had a chemical separation and all of this stuff gets split. All the bonds are taken away and I just have a bunch of carbons sitting around and some hydrogens and some oxygens. Now, we will eventually find that a carbon atom and an oxygen atom and a hydrogen atom are not just solid pieces. They have little individual pieces inside. They have subatomic particles. They are themselves a collection of smaller pieces, just the way a molecule is a collection of smaller pieces. A chemical separation generally cannot split a carbon atom into pieces, cannot split a hydrogen atom into pieces. Okay? We can't do that with chemical forces. We can with a nuclear reactor. So a nuclear reaction is required to split apart an atom into its subatomic particles. So we're kind of getting into different categories here, and there's going to be like a whole unit on each of these topics, okay? So we will go deeper in the future. But that kind of sets up our categories. So you have subatomic particles. The ones we're going to get to are like protons and neutrons and electrons, okay? Subatomic particles. And all of these things will squeeze together into one form. So we'll get a bunch of protons, let's say like in a helium atom, a proton, a couple protons, a couple neutrons, a couple electrons. And as one big chunk, subatomic particles form atoms. And I could have a bunch of helium atoms, right? They would each look the same. And then, or carbon atoms, or hydrogen atoms, or whatever. And from there, you could take a bunch of atoms and stick them onto each other with chemical bonds to form, you know, like I had before. Let's do a bunch of atoms bonded together. This is like the gas that comes out of your stove. This is methane. And this chunk, as one big chunk, would be called a molecule. And you can even put a bunch of molecules together. So, for instance, you could take a balloon and fill it with methane molecules. So here's like a balloon that you tie off, and here's a chemically bonded methane molecule over here, and here's another one over here. And this molecule would be bouncing around in this molecule. There'd be tons of them in there, right? Bouncing around inside the balloon. So you put a bunch of molecules into a balloon. Sometimes you would call this a substance. If it was all methane, if there was nothing besides methane, you would call this a pure substance. You could mix it. You could mix it with some air. What if you filled the balloon with air instead? So from molecules, you could take the balloon. Air is mostly this stuff. It's mostly nitrogen, but it's got some oxygen in it, and it's got some carbon dioxide in it. So those are different types of molecules inside of a balloon. We would call that not a pure substance. Sorry, we would call that a mixture. Okay? And these are like individual molecules. And you can even break down mixtures further, which we're going to do here in a second. So here's the idea. If I wanted to take the gases out of this balloon and separate them out and put the nitrogens in one spot, maybe put them in their own balloon, and put the oxygens in their spot, put them in their own balloon, okay, and put the CO2s in their spot. I could do that sort of the same way I tore the paper. Maybe not exactly the same way. Maybe I'm not going to grab them with my hand, but the way to separate them would be through physical means, okay? And there are several different techniques for doing that kind of stuff, all right? But I wouldn't be breaking any bonds, and I would be just separating out molecules, okay? If I wanted to take a molecule like this, and that's carbon and hydrogen, and I wanted to split that bond apart to just get a single carbon and a single hydrogen, to turn them back into atoms, that requires a chemical separation. That requires physically, or not physically, it requires chemically breaking those bonds. If I wanted to take the atoms, each of these atoms, the carbon and the hydrogen, are made up of a bunch of protons, neutrons, and electrons, and I want to split them into individual protons or individual electrons, I would need a nuclear force. I would need some kind of nuclear reaction to make that happen. Okay, that's kind of the tree here. So now we can start trying to define, so we can get some more definitions here. So atoms, or let's talk about elements. Elements are all one kind of atom. You have some substance, some piece of matter, and if you look at every single atom in that substance, it is always the same atom. So for instance, if I pulled the nitrogen out of air and I just had a balloon of pure nitrogen, nothing but nitrogen, those would all be, that would be a pure element, because it didn't have any other type of atom but nitrogen. Okay? Compounds are molecules, they are more than one atom type that are chemically bonded. An example of that here was the CO2. That's carbon atom, that's oxygen atom, that's an oxygen atom, and they're all bonded into one big piece. That's a single piece, but that single piece is composed of different types of atoms. Whereas this nitrogen was more than one piece, right? It had two nitrogen atoms bonded together, but they were both nitrogen atoms, whereas these are not all oxygen atoms, these are not all carbon. So to be a compound, you have to have more than one type of atom. Okay. Now, among elements, we can further delineate those. So we talked about nitrogen as an element, right, because it contains only N atoms. Well, what about gold? Gold has something like this. Gold doesn't stick to itself, not the same way nitrogen does anyway, or carbon. Well, maybe carbon's a bad example, but helium would be a good example. Suppose we had a bunch of heliums just floating around, which is what helium does. They don't actually bond to each other the way nitrogen bonds to itself. So these are all elements. This would be elemental nitrogen. This would be elemental gold. These would be elemental heliums. However, this helium is technically an atom of helium, and this nitrogen is 2 atoms or 1 molecule of nitrogen. So atoms are single pieces. And if you tried to break them down further, you would have to use a nuclear reactor. You would have to split the protons and neutrons apart. Molecules are multiple atoms bonded. So this is actually similar. So let's look at the similarities and differences between a molecule and a compound. A compound was more than 1 atom chemically bonded. A molecule is multiple atoms chemically bonded. What's the difference? Well, the difference is that a compound has to have different types of atoms in the one compound. So the compound had, this is a molecule, let's say, of CO2. This is a molecule of nitrogen, but the difference is the nitrogen are the same atoms and the CO2 are multiple types of atoms. So all compounds are molecules because they have multiple atoms. Not all molecules are compounds, right? Nitrogen is a molecule, but it's not a compound because it doesn't have more than one type of atom. Okay? Now, let's go to mixtures. Mixtures, to remind us, are multiple, and I'll put particles. Anything can be a particle. An atom is a particle. A molecule is a particle. A compound is a particle. A particle is a distinct unit that just moves on its own, like it's all one contained piece. So a mixture is multiple particles not bonded with each other. I mean, you could have, for instance, let's do a mixture here, like air. We said air is a mixture of mostly nitrogen, some oxygen, and some CO2. There's other stuff. For instance, there's some argon. So when you take a breath of air, you're getting a molecule of nitrogen, a molecule of oxygen. Remember, there's multiple atoms. A compound molecule of CO2, an atom of argon. Now, I don't mean to say you get one of each of these, but you're getting atoms of argon, molecules of CO2, which are also compounds, and then molecules of oxygen and molecules of nitrogen. So there's all these terms that apply to all of them. This is an atom. This is also an element because it's on its own, right? It's the only atom of its kind. This is a molecule, which is made up of nitrogen atoms. It is also an element because all the atoms are the same. This is a molecule. But it's a compound as well because it's not all the same type of atom. You would definitely not call it an element. Okay? That's a mixture. And we have several types of mixtures. We're going to look at a couple here. If the mixture is something that mixes uniformly, like air. When I look at air, I don't see all the different phases. In fact, you don't even really see air. So air is maybe not a great one. Let's talk about a lemonade mixture. You're going to take a liquid like some water, and you're going to dump some lemonade powder into it. Imagine that's your lemonade powder. And you mix it all up, and when you're done, it's a little darker. But it's got, maybe it's like that yellowish color or pink color if you do like pink lemonade. We'll call it a mixture. Lemonade is a mixture of different stuff. It's sugar molecules, it's lemon powder that's sour, and it's water. And there's all those molecules all bouncing around, swimming around in the same drink. And it's pretty uniformly distributed. Uniform meaning it's the same everywhere. If I took a sip of this or this or this, if any drop I pull out of that probably tastes the same. So uniform mixtures are called homogeneous. Okay? Homogeneity is referring to the fact that every little piece looks like every other little piece. Okay? Compare that, let's say, with a chocolate chip cookie. Now, that's a mixture as well. But when I look at it, there's a distinction between this part of the cookie and this part of the cookie. Like this part is the sugar, egg, flour mixture part, and this part is the chocolate chip part, and those happen to be mixed into the same one big piece, but it's not homogeneous, right? If I bit off that chunk here, it would taste different than if I bit off that chunk there, because one of them has a chocolate chip in it and one of them doesn't. So when you can see the different, what we call phases of the mixture, we say it's heterogeneous. So non-uniform mixtures. They're not the same everywhere. Are called heterogeneous. Okay? And that should give us all sort of a common language to talk about all of these different types of matter. Again, the main point is that if you're some kind of mixture, generally speaking, you can separate a mixture with some kind of physical means. We don't have to break any chemical bonds to separate a mixture. I could pick the chocolate chips off the cookie, for instance. If I wanted to separate out atoms from molecules, like I want to burn the paper, that requires a chemical reaction, like burning, right? I have to introduce some chemicals to do the work for me. And if I want to split atoms apart, that's going to require some kind of nuclear force. Okay?